now.
Okay, so this talk is essentially just a summary of my undergraduate dissertation that was titled "The Mathematical Properties of Neural Networks Trained on Artificial Datasets." So to generally explain what was the aim and the purpose behind this, well, the understanding from a technical point of view of neural networks is obviously not really complete, considering the neural network verification and the general understanding of how the process works and is influenced by different factors. And specifically, this project was supposed to add to that understanding by investigating the connection between the range of properties of the input data and the properties of the neural network that is trained on the data, looking for some sort of dependency between one and the other. And to this end, an artificial dataset was used that is called a spiral dataset. It was mostly chosen for two reasons. Firstly, because it is quite challenging to many classifiers. And secondly, because those are two Archimedean spirals with the same point of origin. So they are very easy to mathematically describe and control by parameters. So we generally have three parameters: the entanglement, codimensionality, and distance between spirals, with the most important one here being the entanglement, which is essentially a complexity proxy. Increasing it increases how what is the maximum angle of the spiral, how far it goes. And yeah, this is the one that is used most throughout. Just before I go into any details, the networks used in here are multi-layer feed-forward neural networks that are fully connected with different parameters for different experiments, but I'll go back to it. It's just this is what is used in all of the experiments. And since we're using this type of networks, the output of every single neuron can be explicitly defined mathematically here. And the core of this equation really is the sum over the product of input and a corresponding weight to that input in the neuron. Really, from this, it's generally clear that the weight matrix and the weights of the neural network are the core of the decision process that gets updated during training. And so the weight matrix is the first intuitive choice when it comes to the parameter of the neural network that can be analyzed when it comes to the influence of the input on it. Now, the issue with the weight matrix is that it is a matrix, and so at first glance, there is really not much that somebody can tell about it, especially for larger matrices. Even for the ones here that are fairly slow, just looking at it doesn't give us much information. At best, it can be visualized as a heat map, which gives some indication of whether a large or exceedingly small value is present. But even that is pretty hard for larger matrices that are generally involved. And so the intuition was to use some values that can be inferred from a matrix that can be analyzed easily, or easier at least. First of those is Verbenius norm, which is one of the norms of the matrix and is defined as a square root of trace, which is the product of all the diagonal entries in the matrix, and the matrix in question is the multiplication of a matrix and its transpose. This is pretty handy for analysis since it gives a single number, although it does lose a lot of data from the matrix, obviously, since it boils everything to a single number. And so to look into it in more detail, another value that is pretty obvious to analyze are the eigenvalues and eigenvectors, which, well, they bring the additional challenge of being multiple, and so usually a mean would have to be used and etc., but I'll go into that in a second. Generally speaking, the motivation behind both of those is that geometrically they can be interpreted as how far certain values are mapped, stretched, or shrunk, essentially. And since we can look at a neural network as a change of shape and then data density, although that involves then that meaning can be translated there. So large eigenvalues generally would get translated to possible existence of areas in data density which get very sparse or which get very dense. And there has been research showing that this is generally not desirable. It is the best to have the data smoothly disentangled throughout the process without any areas getting very sparse or very dense. Now, ideally, in that we would be analyzing the Jacobian matrix, but of the weight matrix and determinant of it, but that is very computationally heavy, especially for larger matrices. And so eigenvalues bring, and Verbenius norm bring the same meaning to this analysis. And so starting with analysis of the Verbenius norm, there are two sets of experiments using neural networks with different activation functions, hyperbolic tangent and ReLU. All of the networks have been trained on data with increasing complexity here, and then the Verbenius norm of weight matrix at different layers was taken. Unsurprisingly, the general trend is for the Verbenius norm to rise with the complexity of the data set, which would mean that for more complex data sets, the networks do struggle to disentangle the data smoothly, and they do it unevenly. Here as well, all the values generally rise between layers, and the later layers of the network achieve higher values. With some unpredicted behavior here for the network using a hyperbolic tangent, which we will come back later to. And moving on, because the Verbenius norm doesn't give that much information, eigenvalues give much more detail. Now, the issue with eigenvalues is that, first of all, the original matrix has real entries, and so a lot of them were complex. So generally, what I refer to eigenvalues here, it's norm of eigenvalues. And secondly, usually I'd have to use mean or some other thing that I can infer from the eigenvalues, and as there is quite a few of them for every matrix, which is hard to visualize in any way that can be very clear and can enable comparison. Generally, with eigenvalues, there is this similar trend present, with the values getting higher for networks that were trained on more complex data sets, although it's less clear than with the Verbenius norm, and the clear difference between layers is gone as well. So it's not always true that the value for a later layer is higher than the earlier layers. So this generally gives the result is pretty intuitive in that the networks do struggle more to disentangle more complex data sets, and that results in that is indicated by higher values of eigenvalues and higher values of Verbenius norm. However, the interesting thing here is that there is a notable difference between the networks using hyperbolic tangent and ReLU as an activation function. And they were chosen on purpose. ReLU, obviously, because it generally achieves good performance, and there are countless papers that analyze how well it performs in certain things. But on the other hand, the hyperbolic tangent is mathematically more appealing. It is a diffeomorphism, which is a bijection defined for smooth manifolds, essentially, which just gives it a symmetry when it comes to mathematical proofs and etc. Now, the issue with hyperbolic tangent is that it generally did struggle with this classification, even just looking at the accuracy, which is not maybe the greatest parameter to be judging the worth of the network on, but it is a good initial one. We can see here at least that ReLU generally performs well even for small networks, while TANH has a very uneven accuracy for smaller ones and requires much more neurons in a single hidden layer. So this determined generally the size of the network rather than ReLU. But to look more closely into what the actual influence is of the activation function on the network and the classification process, next set of experiments involved looking at the point mapping. So this used a very small network that one of the layers had 2 neurons, so that we could look at how during the process of training the points were getting moved. Obviously, the end goal of the network would be to make the 2 groups linearly separable, but interestingly enough, they go about it a completely different way depending on the activation function. So TANA generally seems to treat the classes equally, although we can see from here why it would struggle to classify them well if this is the approach, since this generally the only difference during training and depending on batch size is the length and position of those sort of lines. The rest stays similar. ReLU, which is definitely better at linearly separating them and quicker, but it does have a very unequal class treatment. One of the classes gets blown up and the other gets depreciated almost to a point. And well, this is interesting because I haven't seen anything that would compare the influence of activation functions kind of in depth side by side. But the question is whether this sort of unequal class treatment has any negative or positive influence on any other parameters of the neural network. And to look at that more closely and see if it has any negative consequences, before I move into that, there is also a similarity, despite a complete different shape of how the points are mapped. I also looked at essentially how they treat different regions of the spiral. So what we have here is the points is the distance between the final point that it gets mapped to after the training and the original one. And depending on the distance from origin in the spiral. So these are the points that are close to the center at the very beginning, and these are the points that were close to the very end. So both types of networks generally have the same tendency of moving the points that are closer to the outer edges of the spiral most, and moving the ones that are closest to the center the least, which is, interestingly enough, probably similar to how a human would disentangle a spiral. So despite a completely different shape, they are at least similar in how they treat different regions of the spiral. And yeah, to look more closely at how whether this sort of change in behavior does have other effect, I looked at robustness. Now, this is the definition from the paper that Matthew was referring to, the writing rebuttal form. Now, that was a few weeks ago, so probably you all have seen it. In general terms, it's just how far the point can be mapped, which is epsilon, from its original point, that we can guarantee that the network is still going to classify it properly, which was the definition that most suited this work. Essentially, it made most sense. So I first looked at the robustness of the network against random noise, just adding some distance randomized to all the to both the spirals. But both networks performed very similarly and pretty well, so there wasn't really anything interesting happening here. So I moved on to adversarial examples using different algorithms, mostly basic iterative method, and I tested them against adversarial examples that have been given different leeway when it comes to how far they could map the points. Essentially, the final entries here were allowed to pretty much map the points to the exact opposite spiral. So the very low accuracy was expected, since the algorithm could literally map the points to the opposite class. However, while they do perform differently on different examples, and they do not behave exactly the same, there does not seem to be a clear connection between the clear influence of the behavior observed before on the robustness. So the unequal class treatment does not seem to impact the robustness in any negative way or positive way. And finally, when it comes to robustness, I have also come back to the idea from the beginning, that is looking at the complexity of the data set in relation to that, since there has been a link discovered between the ability to generalize to new data and the complexity of decision boundary, and also a link between essentially the complexity of the data set and complexity of the decision boundary. And so I've run the same tests on networks trained on data sets of different complexity. generally at a first glance, we can see that there is the decision boundary does seem to be more jagged or more complex for more complex data sets. It can be seen both here and here, maybe less for ReLU, at least on images this size, which would generally support the theory I was basing this idea on. Although to get any more conclusive results, there would have to be more experiments that would involve more mathematical definition of what the actual complexity of the decision boundary means, since I haven't involved that. And that is generally everything. I suppose everything, or the code that was used here, is available as a tool, well, on GitHub, if anyone wants to look at it. But yeah, this is everything. Thank you. If you have any